We'll be covering force recovery for the stiffness method. We're looking at this with an example for continuous beams, but the method itself is pretty general and will be applicable to all kinds of structures. Let's start reminding ourselves about our example problem and about the method. First, looking at the problem statement. We have a two-span beam, 3 degrees of freedom, which are rotations at all of the nodes, a uniform load of 2 kips per foot applied to both spans, and even lengths for both spans. In the procedure that we went over in a previous video, we started by displacing each degree of freedom in turn, maintaining the other ones unmoved, and seeing what forces are generated by those displacements. Here I've shown the forces that we previously determined for degrees of freedom 1, 2, and 3. The quantities m1 and m2 are 4EI over L and 2EI over L. After taking into consideration how the structure responds to movement of its degrees of freedom, which is independent of the loading, we looked at the applied load. These are the fixed end forces that we previously determined, and the value m3 is 66 2/3 kip feet. From equilibrium considerations at each of the degrees of freedom, we eventually arrived at this matrix solution. K is the stiffness matrix, U is the vector of unknown displacements, and P is the vector of known loads from either member or nodal forces, which in this case are the rotations theta at each of the nodes, can be thought of as a scaling factor for each degree of freedom. Having the problem set up in this way, P equals KU allows us to easily solve for the unknown displacements U as U equals K inverse P, from which we find these numerical values. Graphically, this is what the displacements look like. The positive sign convention was counterclockwise positive, so the negative number means a clockwise rotation at joint 1, and here we have a counterclockwise rotation at node 3. What we need to do here is to determine the member forces, shears, and moments primarily. We'll go over 2 different methods, one method in this video and one method in the subsequent video. The first method is scaling all of the free body diagrams and then adding up all the scaled free body diagrams. This method uses a lot of the previous results that we already had, but it does require a lot of drawing and is fairly difficult to automate. So like any method, it has its pluses and minuses. Let's start by looking at this method graphically. We take the forces generated from degree of freedom 1, multiply that by the scaling factor, the now known rotation at degree of freedom 1. Add to that the forces due to degree of freedom 2 times the scaling factor of the now known rotation at degree of freedom 2. Add to that the forces due to rotation at degree of freedom 3 times the scaling factor of the now known rotation at that degree of freedom, plus the fixed end forces from the applied load and the applied load itself. That will give us enough information from which we can compute now shear and moment at any point in the member. Looking at this numerically, I'm substituting here 4EI over 20 and 2EI over 20 for M1 and M2. These were previously calculated. I'm substituting the number minus 16.6 times 20 over EI for theta 1. That was previously calculated. For degree of freedom 2, we've substituted for all the moments, but that's not really all that important because the rotation at that degree of freedom is 0, so everything is going to be zeroed out. For degree of freedom 3, we've again substituted for the 2 moments M1 and M2, multiplied by the now known displacement of 16.6 times 20 over EI, and added in the forces due to the applied load. This is the value for M3 that was also previously calculated. I'm not displaying units in any of these calculations, but all calculations are consistent in kips and feet. Taking the results we just calculated, we can do this sum and see what it comes out to. Looking at the first row, just performing the multiplication gives us these moments on the member. I've now stopped showing the moments on the joint. It's a lot of drawing, and it doesn't have any additional information that we can't find from what I've drawn here. Now so far, I haven't shown the shears. For beams, if there's no translational degree of freedom, I don't need to show the shears. But now that I'm worried about member forces, I need to recover the shears. The way that I think about this is as follows. These moments of 33.3 and 66.6 are both acting in a clockwise direction. That means that the shears must act in a counterclockwise direction. The total moment 66.6 and 33.3 is 100. 100 divided by the member length is 5. And so I show shears of 5 that are acting to produce a moment in the counterclockwise direction. One more aspect to mention here. The rotation for degree of freedom 2 was a negative, and you'll notice that this moment is drawn on the member in a negative moment direction. But when I take that and draw it over here and incorporate the negative sign, I'm now showing this moment in a positive bending direction. So we see how the sign of the displacement influences the answer. Moving on to degree of freedom 2, there's nothing to show because the scaling factor is 0. Moving on to degree of freedom 3, it's a very similar explanation to degree of freedom 2. There's no negative sign, so the arrows maintain the same orientation. The applied moments at the end of the members tend to rotate the member counterclockwise. The shears tend to rotate the member clockwise. Add to that the applied forces, the fixed end moments, and now I've also recovered the shear forces here. The applied load of 2 kips per foot times the length of 20 feet is 40 kips. It splits evenly to each side because of symmetry. That gives me a shear force of 20 kips at either end. Continuing with these results, we can then combine all of these together. Let's look at different points of the member. On the left end of the left member, we have a positive moment of 66.6 from DOF1. We have a negative moment of 66.6 from the applied load. That results in 0 moment at the end. That's good, because that's a moment-free end at a pin, so it shouldn't have a moment. Looking at the transverse force at the left end, 5 downward, 20 upward, nets 15 upward. Copy the distributed load straight onto the beam. Transverse force at the right end of the member, 5 upward, 20 upward, nets 25 upward. Moment at the right end of the left member, 33.3 negative, 66.6 negative results in 100 negative. The calculations on the right hand side are very similar. This problem we've seen already when we did the flexibility method, and we arrived at this very same figure. If we draw this together, we have this free body diagram. The 100 kip per foot is equal and opposite on both sides of the cut, so that disappears. The two 25 kip forces vertically upward become a single 50 kip force. And this is the free body diagram that we saw when we did this example in the flexibility method. So given now that we have this free body diagram, we can now determine a shear diagram, we can determine a moment diagram, and so we've finished the problem. This concludes method number 1 of force recovery. In the next video, we'll see method number 2, which is a little bit more algebraically formal. It can be a little bit quicker, but it might be a little bit less intuitive. By seeing 2 different methods, you'll be able to choose and you'll be able to learn different ways.